Hey everyone, today we'll be going over graphs today. Particularly, we will be focusing on building an unweighted graph, and without any further hesitation, let's get started. And now we're going to be going over our weighted graph. Now, first thing that we're going to do to be able to print out our necessary behaviors for our unweighted graph is that we are going to do the following. We're going to create a header file like we did before, and this time we're going to call this unweighted graph printer. I'm going to put this in column for practice, create it. And what I'm going to do now is that we are going to include our libraries. Then we will define our class. And inside of our class, we need to define a public instance. And we are going to have a series of functions. Really, we're going to have 1, 2. So we will have 1, 2, 3 functions in total, which we will have one for printing the graph, and we're going to have 2 private functions. So that way there's no miscalling between when we are putting it inside of our main C++ file, which int main here, and return 0 just for clarification. And our 2 private functions are going to render the graph, and we will also draw the arrows. Now, mind you, always know this is also a directed graph whenever we are drawing arrows, and when we are not drawing arrows, it's considered an undirected graph. So like what we did before, but we're just doing this for the sake of getting fully accustomed with the C++ syntax, so you can code along as well, and we know our full structure entirely. So what we will be doing to include our libraries, we are going to have 1, 2, 3, 4, 5, 6. Include, 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 include. We're gonna have iOS stream. Depending on your IDE, it will be totally different. Then we will have vector. Then we are going to have list. Then we are going to have CMath. Then we are going to have string. And then finally an unordered map. We're going to define our class. We're going to call it, and also don't forget, using namespace std so that we're not using std in multiple instances. And now we're going to have our class called unweighted graph printer. Here we go. Then right here, and have our semicolon. Then we're going to define a public instance right here, public. Then we're going to have our function for printing out the graph. So I'm going to go void print graph, and putting in our vector, because we're going to have our adjacency list of integers in order for us to be able to print out a graph. Constant here. And then what I'm going to be doing is that we're going to output our graph adjacency list. And L, there we go. In fact, I'll just zoom out a little bit so that way we can see everything. There we go. Then we're going to scan through our adjacency list for int v is equal to 0. V is less than the adjacency list size. And we're going to implement, we're going to go through each vertex inside of our adjacency list to be able to output our graph. And we are going to output each vertex accordingly with the respective arrow to highlight the connectivity between the 2 vertices. We're going to have another for auto loop, auto it indicating for iterator, and we're going to be going for the specific vertex inside at the beginning, and then while the iterator is not at the very end of the adjacency list, we're going to keep implementing and incrementing our iterator. Count So that way we can know exactly when we hit the very end. And then we're gonna have count and L, and then count and L, to then output count. We're gonna implement the drawing of our graph edges using ASCII here and L, and then we're gonna do render graph with our adjacency list implemented inside. Now we're gonna have two private functions, so we're gonna call this private. I'm gonna have this function void render graph that we did over here. Then we're going to implement our adjacency list by using constant vector list int and adjacency for constant. And since we are going to be making this graph correspond with each of the edges and vertices accordingly, we're going to put this as a radius. We're going to have a radius of 10. And then a diameter 2 times radius plus 1, and then we're gonna have a vector of strings to indicate for the graph lines, putting it in for diameter string diameter times 2, and putting in each space, and then we're gonna initialize our size based on the adjacency list. So what we did is that we created a vector of strings called graph lines that's going to implement our diameter and the string, and it's going to also have a radius at the same time with respect to the size of our adjacency list eventually. Then we are going to have an unordered map to indicate the key pair values because we have an edge and a vertex accordingly. So we have int pair int indicating for the positions, and for int I is equal to 0, I is less than the size, and we increment I accordingly. Then we are going to consider our angle, double angle, equal 2.0 times m underscore pi times I divided by the size. So we know exactly the specific position when we are outputting, and we're going to have our x-axis equal radius plus the static cast int for radius times cosine angle, and then we will do the same thing for our y. Make sure you're spelling everything correctly. Yep. Now we are going to replace this with y, static cast rate int radius sine angle, and then we will have the positions of I within our adjacency list with respect to the x and y axis as well. Then we're going to have a for loop to indicate where specifically the vertices are going to go. So we're going to have for int v is equal to 0, v is less than the size, and we increment each vertex until we reach the very end of our adjacency list, hence size, which was called upon before over here. And then we're going to have auto x and y equal positions for each vertex that we have, graph lines of y with x times 2 equal our initial right there. Graph lines with y with respect to x times 2 plus 1 equal 0 plus v. 4 into v is equal to 0. V is less than size, and we increment v as well. Then 4 auto w adjacency v with draw arrow, which is going to be our function that we'll have down here. Graph lines, positions v, positions w, which will be indicating for 2 different vertices as well. Hence we have this w right here with respect to adjacency of the vertices inside the adjacency list, because we need to connect 2 vertices with an edge to be able to make a graph. And then we're going to have this 4 constant auto and line with graph lines, count line and L, so we know exactly when we are rendering the following graph. And this is just the real kicker that will help us define how the graph is going to be laid out. Now we're going to draw the arrows, and whenever we have arrows in a graph, it is considered a directed graph. So technically you can combine both of these terms together and say we have a directed unweighted graph, because we don't have any weights inside of our edges. And so void draw arrow, we're going to have vector of strings and graph lines pairing each integer here from, and then pair int to, so we can connect, know where to connect each vertex. Constant right here. Int x1 is going to be from first, y1 is going to be equal from second, there we go. And then we will have int x2 equal to first, and then y2 is going to be equal to second. So we know exactly when to pair each vertex with the respective vertex as well, and then draw the arrow. Then we're going to have our distance, dx equals absolute value of x2 minus x1 with dy is equal to the absolute value of y2 minus y1. And int s of x is equal to, make sure you have your semicolons that we set up in place, x of 1 less than x of 2, or 1 to negative 1. And then int s of y is equal to y1 less than y2, or 1, negative 1 in this case, and then error dx minus dy with the respective exact point. And while everything is already lined up and we have already rendered our graph, what we are going to be doing is determining where to actually draw the arrow, as in the line, and then the actual arrow point. So if x of 1, and so this is where we have our edge cases, so if they're in the same distance, and y of 1 is equal to y of 2, we're going to break, int e2 is equal to error times 2 if e2 is greater than negative dy. We are going to implement, we're going to declare error to be decremented by the distance of y, and then we're going to have x of 1 be the be s of x. then if 2 is less than d of x, error d of x, y1, sy, and then if x of 1 doesn't equal x of 2 or y of 1 doesn't equal y of 2, we're going to have our graph lines with the following parameters of y of 1 and x1 times 2 equal the following arrow dash, and then we're going to have our graph lines with respect to y2, and then x of 2 times 2 equal the actual arrow that we have. And yes, so this is our unweighted graph header file that we will be implementing while we are building out the necessary tasks for our graph, where we need to add an edge, remove a vertex, remove an edge, perform depth first search, and perform breadth first search both iteratively and recursively. So then, moving over here, let me just make sure everything's already built correctly. All right, build succeeded. Now, let's head over and use our header file to then complete the necessary tasks to build out our unweighted graph and the necessary tasks that we need to do. So let's move over. And now we will be focusing on adding an edge for our unweighted graph. Now, to get things off, what we need to do is to build out our entire weighted graph is that we're going to include our libraries. We're going to have a class, and we will have a public instance inside of our class so we can call upon different functions to put inside of our main function as well. And inside of our class, we are going to add an edge, remove a vertex, remove an edge, perform depth first search iteratively, do depth first search recursively, and then we will do the same thing, but we will do breadth first search as well. And so, for us to be able to get started, there are going to be 7 instances. We're going to include different STL libraries and our header file as well. 5, 6, 7. So I'm going to go IO stream, depending on what IDE you use, and maybe different. Then we would do vector. Then we're going to go stack for depth first search, queue for breadth first search, a list, then algorithm, and then we're going to include our header file right over here. .h already set up in place. I also have the links for the GitHub repository in the description below, so that way you could be able to be able to plug and play at the same time. And then also don't forget using namespace std, so we're not using std multiple times. So now we're gonna have our class called unweighted graph, and I'm gonna put this over here. There we go. Now we're gonna have a public instance, so we can call upon different functions, and we're going to initialize our variables, our vertices, which will be int v. Then we're going to have our adjacency list in order to actually pull out our graph. So we're going to have vector list int, and call this adj. Now, for us to be able to add an edge, what we're going to be doing is just do the following: void add edge int v int w, since a graph needs to have 2 vertices and an edge to be able to make the graph a graph. And so we're going to have adjacency v push back for w, since both of them are connecting. And then we're going to have adjacency W pushback for V. So we know that these two are connected. Now we're going to head over to our main function, and then we're going to do the following. We're going to be adding our edges. So also, part 2, we need to add a constructor. And our constructor is going to be the following. It's going to be unweighted graph with int v, respect to v, and adjacency resize as well. For v on the inside, so that way we can call upon our unweighted graph as well. So calling upon our constructor, and we will add an edge to our unweighted graph. So we're going to do unweighted graph, and then I'm going to call this, we can say graph. And since our constructor has a parameter of vertices, we're going to put in a number of vertices, which would be 6 in this case, because this is calling upon v, and then this is our number of vertices as well. So once we have done so, now we're going to add an edge or a series of edges to our unweighted graph. So we're going to go graph, because it's calling upon this variable from our constructor over here. And then we're going to have graph dot, looks like we can add edge over here, and then we're going to have two vertices. So we have 0 and 1, and we're going to have 6 vertices in total. So I have 0, 1, 2, 3, 4, 5. At edge here, 1, 2, 3, 4. Yeah, okay. Let's see what happens. So I have 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, and finally 5, 0. There we go. Now we're going to build this and see if it's all good. And build has succeeded. Now let's print this graph out as well by going through and printing out unweighted graph printer, which we'll be calling upon as printer. And then we will be printing out the graph like this, printer dot print graph, like we did before over here, calling upon this function where we have here print graph, and we'll have our graph dot adjacency list that we're putting in inside of as a parameter. Notice, because we have a vector for our adjacency list that we made already here, and that we have initialized here inside of our class for unweighted graph. So let me build this, make sure it's all good. All right, now let's run this. There we go. And let me just zoom out of here so we can see. And we have our unweighted graph. Notice in particular, we don't have any values like we had before for our weighted graph. And we already see the connectivity between such over what vertex is already connected with which, such as like 0 is connected between 1 and 5. And then we have 1, 0, 2 already connected with 1, 0, 2. So these vertices are really connecting with each other to determine what exactly, what form of connectivity we have in relation with it. And so this was adding an edge. All we did was just, we had a void function of add edge, we had our constructor, we had our vertices as well in several class, then we also added our libraries as well. Now let's move forward to removing a vertex within our unweighted graph. And now we're going to be focusing on removing a vertex from an unweighted graph. So for us to be able to accomplish this, what we are going to do will be the following. We're going to have void remove vertex. We're going to have int v, and then we're going to have for auto and neighbors adjacency with neighbors dot remove v, And then we're going to have adjacency v.clear as well to make sure that our vertex is completely removed from the rest of the graph entirely and separated as a whole. And we do this from a list perspective as well, since that's just about how we curate our data. Now, going down, what I'm going to be doing is that we're going to go and we are going to remove 3 like we did before. So remove vertex, graph dot remove vertex, and we're going to select 3. And then we're going to do the same thing again over here. Make sure you also have your semicolons as well. I'm going to put this at the top. There we go. That's our printer. We add an edge. Now we're going to remove a vertex as well. And we're going to print out our graph. So let me just build it, make sure it's all good. Build succeeded. Run this bad boy. And it looks like we have succeeded in removing 3 from the rest of our unweighted graph as well. We see the connectivity as well as in our graph adjacency list. Nothing else is connected. So this graph adjacency list showcases our graph from a list perspective over what vertices are already connected. And we have removed 3 as accordingly. There we go. And so, yes, this is how we remove a vertex from a graph. Now let's focus on removing an edge from our unweighted graph. So let's put this up here, remove a vertex. Now we're going to head over to remove an edge. And now we're going to be focusing on removing an edge from our unweighted graph. So in order for us to be able to do so, what we are going to do is that we are going to have our function void remove edge, and every single graph has 2 vertices and an edge. So we have int v and int w, indicating for 2 vertices, and then all we got to do is from our adjacency list, adjacency v dot remove w. I'm going to do the same thing, but from w's perspective as well. So adjacency list from w all the way to v. So we remove a following edge as well, and this time we're going to do 4 and 5 in this case when we go back down. So going back down, I'm actually going to put this right. Yeah. So from the same graph. Okay, so I'm just gonna put this right here. Edge. So we're gonna have graph dot remove edge, and we're gonna remove edge 4 and 5. So int 4 and 5, and then we're gonna output the same type of graph that we had before. Make sure you have your semicolons already set in place. Let's build this, make sure it's all good. Build succeeded, and run this. And ta-da, we have removed an edge from 4 and 5, and look at the connectivity. It's also changed dramatically at the same time. So we see our vertices already connected together based on what is connected, like 5 and 0, but not 4. And notice how 3 has already been removed since we have already accomplished that beforehand with removing a vertex. And outputted our updated graph adjacency list as well. We notice the connectivity in total. And now that we have done so, let's go to depth first search iteratively for an unweighted graph. And now we're going to perform depth first search iteratively. So the way we're going to go about this is that we're going to have our function void dfs iterative int v, and then we're going to have a vector of booleans to indicate what has been visited with our following vertex. First initialized, saying that, hey, we have not visited anything yet, and since we are dealing with depth first search, we have a stack of integers, and call that stack. Then we are going to push our first vertex inside of our stack so that way we know exactly what has been visited. And remember, stacks always go last in, first out, just like a stack of plates. And so we have while stack is not empty, we are going to indicate that our first vertex is going to be at the top of our stack, and we're going to pop the stack to output exactly what values we have. And if, and with our edge case, if the following vertex has not been visited, then we're just going to output v, or right here, each vertex accordingly, for we're going to redeclare this as true inside of our Boolean vector as well. And we're going to have a iterative loop of for auto I is equal to the adjacency vector at our beginning, because we're focusing on the rear beginning because stacks operate last in first out, so we start at the top of the stack. Then we're going to have I, while I doesn't equal adjacency vector at the end, or our end, which will be technically the beginning. We're going to increment I as our index, and if the following index has not been visited, then we're just going to push the following value of I into our stack to say, hey, we have already visited and such. And finally, we're going to output at the end. And let me just build this, make sure it's all good. And build has succeeded. Now we're going to go down. And what I will be doing is that we are going to call upon, we're going to just put this output cal DFS iterative starting from vertex 0. And then graph.dfs iterative with 0. There we go. We're going to build this. Build it succeeded. And we have outputted depth first search iterative starting at vertex 0, but we also need to remind ourselves that we first need to add the following edges as well, and after we have printed the graph. So build this, then this is here, and then we get the following values 0, 1, 2, 3, and 4. I'm just going to put a space right here, build this, run it again, and then we have the following vertices already outputted, already set in place. So yes, right here. So that was depth first search, since we're focusing on the levels of what has been added. And now let's head over and focus on implementing depth first search recursively as well. And now we're going to go through depth first search recursively. So the way we're going to build about this is that recursion typically uses principles of a function inside of a function. So what we will do is that we're going to have a helper function, and then we will have our actual function we will call. So our helper function is going to be the following. So void dfs recursive for int v and then vector of booleans, and indicating what has been visited. Then what we're going to do is that we're going to have visited for each vertex indicated as true. Then we're going to output each vertex accordingly. Then for auto I, alright, yeah, focuses on each vertex at the beginning, and then we will have I, while I doesn't equal to the last vector at the very end. We're going to keep incrementing our index, or iterate, whatever, and then if it has not, if a vertex has not been visited with our indicator, then we're going to call upon this function here to be of I visited there. And then we're going to have our actual function that we call with void dfs recursive start int v, and then we're going to have a vector of booleans indicating what has been visited, and initializing with our vertex that we have initialized at the top with false, and we are going to call upon this function right here for each vertex, and we're going to indicate what has been visited and what hasn't. And then we're just going to output at the very end for each one. Let me just build this to make sure. Build has succeeded, and the way we're going to call upon this inside of our main function will be the following. All we need to do is we need to recursive starting from vertex 0, and instead of dfs iterative, we're going to go dfs recursive start at 0, since we're using this function, which is already putting in the principle of recursion of calling the function inside of a function and keep looping it inside of itself. So now I'm just going to build this, make sure it's all good. Build has succeeded, and we get the same output. So this is depth first search in a recursive manner, and all we did was just we had a different design pattern compared to what we did with iterative depth first search. So this is depth first search recursive. Now that we have already implemented depth first search for our unweighted graph, now let's focus on breadth first search for our unweighted graph in total, for iteratively and recursive. And now we're going to do breadth first search iteratively. So the way we're going to go about this is that we're going to go void breadth first search iterative int v, set up for vector boolean for visited, indicating for each vertex, and have that as false because we have not visited anything. And since we're dealing with breadth first search, we always do a queue of integers in this case, and we're gonna label this q. Then we're gonna have visited for v is gonna be equal to true. Then we're gonna push each vertex inside of our queue. Now queues operate based on first in, first out, like a grocery store queue. And while the queue is not empty, we're gonna have v equal q dot front, which would be retrieving the vertex at the very front, and output each vertex accordingly. And then we are gonna pop the queue, so that way we know exactly that it has been visited. And now what we are going to do throughout our adjacency list is that we are going to scan for auto I, which is our index, adjacency v at the beginning, since we're not dealing it with our begin like we did with the stack. Stack operates by LIFO, and while the iterator doesn't equal adjacency at the end, we're going to increment I. Now, if the following iterator in the adjacency list has not been visited, then what we're going to do is that we're going to indicate that now it has been visited. I is going to be indicated as true, and then we're going to push the actual index that we have found throughout our adjacency list inside of the queue. So we say, hey, this has already been visited, and now we'll implement this at the end. Now let me just build this to make sure it runs good. And build succeeded. Now we're going to go down, and what we are going to do is that we're going to do the same thing we did for depth first search, but we're going to do this with breadth first search. And we're just going to call upon this function that we have over here. I'm going to put this down here, and since we are starting from vertex 0, it already makes sense. You can also do dot BFS iterative, and you'll see it come up depending on which IDE you use. So let me just build this, make sure it's all good. Now let me run this. And this is what we get for our breadth first search from an iterative perspective. It does what is expected for our following outputs, because breadth first search goes based on levels, while depth first search goes on the depth of the following graph as well. Hence why we have different outputs with our respective vertices. So it's like, for instance, we have 0, then we have 1, and we also have 5. Let me see if I can zoom out of this to indicate the example, and then move this up more. So for breadth first search, again, 0, 1, and 5, 0, 1, and 5. Then we see 2 and 4, and finally 3. So we see the following graph go from 0, 1, 5, 2, 4, and then finally 3, as indicated, as well as the order of the following vertices at the same time. So yeah, this was iterative breadth first search, and finally, let's go over doing breadth first search recursively. And now we're going to perform breadth first search recursively. So the way we're going to do this is that we always know that recursion typically has two functions, two functions really, where we are going to have our helper function and then the function we call, just based on the principles of recursion. So void breadth first search. So this is going to be our helper function, recursive for q int and q. Then we're going to have a vector of booleans, and indicated what has been visited. Let me just zoom out here. There we go. That's better. Now, with that, we are going to say, hey, if the queue is empty as an edge case, then we are just going to simply return saying, hey, there's nothing in there. Then we're going to initialize each vertex at the queue's front. And then we're going to keep popping the queue to determine exactly, hey, this is a vertex that we have visited, and we're just going to output the following right here. And then we're going to scan through our adjacency list for auto I. It's going to be the adjacency vertex at the beginning. Then if the adjacency, if the index is not at the end of the adjacency list, then we're just going to keep incrementing our index until we reach the very end. And we are going to say, hey, if this index in the adjacency list has not been visited, then we are going to say visited I will be indicated as true because we're dealing with a boolean over here to indicate, like saying, hey, this has been visited. Make sure you spell everything correctly. There we go. And then we're just going to push the following iterator inside of our queue or index value, I would say. Hence the star I. And then what we are going to be doing is that we're just going to keep calling upon this function for visited right here. And that way it's just going in that loop, hence principles of recursion. Now, the next part will be the other function that we will have, the function we will call. So void BFS recursive at the very start. We'll have a vertex on the inside indicated as parameter v, lowercase. Then we're going to have a vector of booleans indicated what has been visited. For the vertex we have initialized at the top, right here, going down, and then saying, hey, we have not visited anything yet, but we're going to, and then we're going to have our queue that we are going to make, call this queue. This is how we make this tool, and then we're going to have visited for each vertex indicated as true, since we were dealing with Boolean vector. So it's literally taking this, saying, hey, the following vertex in the following parameter that we have inside of our vector is going to be indicated as true, since each vertex is going to have a condition true or false for our vector, since we already have a pair of the integer value and indicating whether or not it's true or false. Then we're going to push each vertex inside of our queue, and then we are going to call upon our helper function on the inside that we have made. Let me get a few of that. Recursive, and then we're going to put in queue and then visited as well, hence the parameters of the queue that we have, and then the vector, the Boolean vector as well. And don't forget your semicolons, and then finally we're going to output at the end. Now let me just build this to make sure this is all good. Build succeeded. Well, we're not going to run anything yet because we need to go down, and all we have to do is that we're going to do the same thing that we did over here, except we're going to do recursion. Breadth first search recursive starting at the vertex 0, and that means BFS recursive start, because this is the function that we have that's going to call upon this function for principles of recursion and just keep everything tidy per se. People would actually have a bit of an argument saying recursion is easier to put in and implement, so that way one knows exactly what to be able to output. Now I'm going to run this. And we get the same output that we have from our iterative. We just designed it differently with a different pattern of design called recursion. And let me just go up, and hence we already know exactly the format, because breadth first search goes based on level. So we see a 0, 1, 5. Look at that, 0, 1, 5. And then we see 2 and 4, 2 and 4, and finally 3 is indicated over here. And that would be breadth first search, because breadth first search goes on levels, and depth first search goes on depth for the graph. And so, yes, this was Breadth First Search Recursive overall. And now let's go over a brief overview for unweighted graph, knowing the exact definition of such and how it compares with our other graphs as well. And now to go over what we have built entirely. So first off, what we did entirely for unweighted graph is that we made an unweighted graph printer header file where we included our necessary libraries, define a class, have a public instance to print the graph that will be called upon when we are printing out the necessary graph as well. In the case of removing, and then a vertex and an edge, and the overall graph as well, indicated down here in our terminal output. And then we had two private functions to render the graph and draw the arrow that we have also called upon to be able to actually print out the direction of the graph. So technically this would be a directed unweighted graph, since we have the combination of directed, which is indicated by the arrows, then we have unweighted because there is no value, or there are no values on the edges as well. So you can also get rid of the arrows at the same time. You would not need this, and you would still get the same output, and therefore get an undirected, unweighted graph as well. And then inside of our main file, so what we have done for the following is that after we have included our libraries, and then also using namespace std, we have a class called unweighted graph, where we built out our variables, and we have a constructor that we're able to call upon inside of our main function as well to be able to build out our necessary vertices as well, since it is indicated as a parameter at the top over here. Then we add an edge, as we have indicated by putting respective with vertex v and vertex w as well, so that way we're able to output our following graph adjacency list and be able to perform depth first search and breadth first search both iteratively and recursively. Then we removed a vertex as going down and further. Right over here, we have 3 in this case that we have already removed, and then we also removed an edge at the same time, going down here, since we removed an edge by doing the same type of principle that we did with adding an edge, except for we called upon remove within the vector STL library. And also, when we remove a vertex, we have neighbors as a bit of a function as well, where once we remove the following neighbors of a vertex, we're able to use our adjacency file to be able to clear inside of the adjacency list. So that way we're able to isolate and fully separate that vertex at the same time. Notice the similarities of what we did before, except for we called upon different functions from the vector library. Then, when we performed depth first search iteratively, what we did is that we just had one function that we would use, and we use a stack, since stacks operate based on LIFO, last in first out, and we push each vertex inside, and then while indicating that, saying, hey, while the stack is not empty, we have to check the top of the stack, and then we're going to pop it. And when we are checking the vertex that is inside of the stack, if it has not been visited, we're going to indicate and output that this vertex will be listed out accordingly, and then we're going to reiterate. Make sure as well, but they're all spelled correctly, so make sure at the same time that it is also that you are also spelling everything correctly as well, so that way that makes sense over here. And then you'll have a for auto loop to indicate exactly throughout the rest of the adjacency list, saying, hey, at the beginning, but since we are operating with stacks, stacks operate based on the top, and then at the end, because that means go for the bottom of the stack, like a stack of plates, just visualizing like that. Then we're going to push our index value, saying, hey, if this following index value has not been visited, we're going to push it inside of our stack to therefore check in particular of when the following has been visited, and then we're just going to output the following at the same time. So that's the iterative. And then recursion operates based on two principles of really just using two functions in general, and indicating and re-indicating that, hey, is a vertex is visited, then we're going to output the following. And then with that, we're also going to use a for auto loop to be able to check through our adjacency list to see if it has been visited or not been visited. And if it has not been visited, then we're going to put the indicator at the top, so that way we can declare saying, hey, we visited it again, and we're going to output the vertex as well. And we used a start function to be able to call upon inside of our main class overall. Since principles of recursion typically use a helper function and a function inside of a function, since if we were to go up, we notice that our actual function that we call uses the helper function that we made over here. And yeah, that would output def for search accordingly in the same instances and values that we have. Now, the differences between breadth for search and depth for search is that breadth for search operates based on FIFO, first in, first out, like a grocery store queue for the most part. And what we use is that we use a vector to indicate that what has been visited and what has not been visited, since we have a vertex right here that we use for the top. And right here, then going all the way down, indicate what has not been visited. Then we initialize our queue. Then we're going to say, hey, the vertex that we have implemented inside of our vector is going to be set to true now, even though we have initialized it false. It's just the first vertex that we have already implemented from our parameter. It's going to say, hey, we first visited. Then we're going to push that inside of our queue. And while the queue is not empty, we're going to check the front of the queue, since queues operate based on first in, first out. And we're going to output each vertex accordingly and keep popping it, saying, hey, this has already been visited. Then we're going to keep scanning through our adjacency list to indicate at the beginning, and then we're going to have an index over here at the start of the beginning, and then an index at while the index is not approached the end, we're going to increment, indicating that if the index has not been visited, we're going to say, hey, this is true, and then we're going to push our following index value, hence star I, inside of the queue to therefore see, hey, what has been visited and what has not been visited. And we're just going to keep doing that until it actually reaches at the very end. So this is just iterative. It's just one function, one go. And yeah, there are no helper functions as well. People like iterative, people like recursion. It really depends what you're working with. And then recursion operates the same thing that we did for depth first search. Except for differences is that we're operating based out of a queue, have the following parameters, and then also our Boolean vector as well, indicating what has been visited, what has not been visited. And if the queue is empty, we say return. Then we check the front of the queue, and then we pop it, printing out each vertex. And then we use a for auto loop to scan through our adjacency list at the beginning. And if the index is not approached at the end of the queue, which means the very front, sorry, at the very back, because queues operate first in, first out. Then we're going to keep implementing our index, and then if the value of our if the following value from our adjacency list is therefore not been visited, we're going to say that now it has been visited, and we're going to push the value inside of our queue, and we're going to use this function to loop around and keep implementing accordingly, indicating what has been visited, what has not been visited, already set up in place. So we use the vector to sort of keep track of everything, saying what has been visited, what has not been visited, and use the queue to be able to actually output everything that has been visited. So it's a type of data structure that we use to be able to actually output our following values, and breadth for search is a type of algorithm that we use to be able to actually move forward and be able to keep track of our following values. Then we have a recursion, breadth for search recursion start. It calls upon the function breadth for search recursive. Hold on, there we go. Calls upon our function that we have over here after we have initialized our Boolean vector and our queue as well, since it is a parameter of queue and Boolean vector. Then we're going to push our following vertex that we have, since we have vertex as a parameter over here inside of our queue, saying, hey, what is this value, has been visited, not been visited. Then we use breadth for search recursive to indicate and run through our logic necessary. Since this is our helper function, this is the actual function we call. And people like this because it can be easier to implement compared to iterative, depending on the complexity of our tasks. So you would do that, the following output at the end. And then we have done so already here. Breadth for search, and we notice the difference that we have already made, 0, 1, 5, 2, and 4, since breadth for search goes based on level. Already here. We notice, to be able to start, notice the pattern of 0, 0, 1, 1, 5, 5, then 2, 4, and 3. Look, 0, 1, 5, 2, 4, and 3. I'll do it again. 0, 1, 5, 2, 4, and 3. 0, 1, 5, 2, 4, and 3. So, there we go. implement it like that. I'm going to zoom in for the sake of it. And yeah, so this was building out our unweighted graph. We noticed particular principles that we have combined, such as a directed unweighted graph, because we have arrows in this case, and if it was an undirected unweighted graph, it would not have arrows and would not have values on their edges. Really, the principle of unweighted is that, hey, this graph has no values on the following edges, unlike a weighted graph as well. So that's a key indication that we have. And now we have already finished our unweighted graph, let's head over and focus on cyclic graph as well, and then we will see how well it compares with other graphs at the same time. So yes, I also have the links in the description as well from our GitHub repository, so feel free to play around with the code at the same time, but it's also great practice to be able to code along and actually understand the whole principles behind such. So yes. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe, and if you do have any other questions or suggestions, please put them in the comment section, and as always, take care. Cheers. Bye-bye.